Most .NET developers start by building standard N-tier applications. You stack a presentation layer on top of a business logic layer, which sits directly on top of a data access layer. Initially, this stacked approach makes sense, but as the project grows, the system often falls into a state of tight coupling. Your core business rules become physically wired to a specific object relational mapper, like Entity Framework Core. As this diagram shows, if you need to swap SQL Server for MongoDB or scale a feature independently, you can't. Replacing the database layer triggers a chain reaction of cascading errors that forces changes all the way up through the business and presentation layers. When foundational technical details shift under pressure, the structural integrity of a tightly coupled system fails. You must tear down and rebuild. Onion architecture, and the closely related clean architecture, provides a structural alternative to this problem. The core principle is that business rules must be entirely isolated. They should function without any knowledge of how data is saved, cached, or transmitted over the network. By flipping the traditional dependency model, you stop writing scripts that break when technical requirements change, and you begin engineering systems where components can be swapped or scaled independently. To understand how the onion model actually functions, you have to separate two concepts: compile time project references, which code physically points to which, and runtime execution flow. Think of your application layer as a television and your database as a power plant. If you physically hardwire the television directly to one specific power plant, your TV is entirely dependent on that facility. If the plant goes down or changes its voltage, the TV becomes useless. Instead, engineers build a standard three-prong plug on the TV. This plug is an interface. The television doesn't need to know if the power comes from a nuclear plant, a solar panel, or a battery, as long as the source fits the plug. In .NET code, the application layer defines that interface. The infrastructure layer is then responsible for creating the specific implementation that fulfills it. By forcing the infrastructure to plug into the application rather than the reverse, your business logic dictates the requirements and remains functional regardless of the underlying data source. We visualize this in .NET as 4 distinct project layers. At the very center is the domain layer. This is a pure C# class library. Its most important characteristic is that it has absolutely zero external dependencies. It holds the core business entities and repository interfaces. It has no knowledge of databases. Wrapping around the domain is the application layer. This acts as the manager, orchestrating business use cases, and it only references inward. Here, you define your data transfer objects and the interfaces that external technical tools will eventually need to implement. The application layer dictates what needs to happen, but it never contains the code for how the technical details are executed. This isolation lets you unit test complex business rules without a database. Moving outward, we reach the infrastructure layer, where technical implementation details live. It references the application layer for interfaces. This is the home for your external API clients, file storage services, and Entity Framework Core migrations. Crucially, the DB context lives here, preventing core logic from tying to a specific mapper. The final outer ring is the presentation layer. This is the system's entry point, such as a web API. The web API references the application layer to trigger business services, but its reference to the infrastructure layer is used only for setting up dependencies at startup. Under this model, controllers never interact with the DB context directly. Isolating volatile frameworks to the outermost edges means you can update database engines or UI frameworks with minimal impact on the core logic. While these layers are separate at compile time, dependency injection acts as the glue that connects them when the application is actually running. Clean design uses extension methods within the application and infrastructure layers to handle their own registrations, keeping the API's main startup file clean and manageable. At runtime, the DI container is an assembly line. The controller requests an I-order service. The container builds this service, which demands a repository from the infrastructure layer. It injects a DB context into the repository, then hands the assembled chain to the controller. Using the scoped lifecycle for these services ensures that a single DB context instance exists only for the duration of the HTTP request, optimizing memory usage. The DI container manages the complexity of object instantiation, letting you write decoupled code that snaps together dynamically at runtime. This architecture provides the most value when an application faces performance bottlenecks in production. Because the system is decoupled, you can often solve performance issues by adding new components rather than modifying existing core logic. For example, imagine database reads become too slow and you need to implement a caching strategy. Using the decorator pattern, you can wrap your existing SQL repository inside a new cached repository. The data flow hits this new shell first. The system checks the cache, and if it's empty, it falls back to the database. The application layer continues calling the same interface, unaware that a caching layer was even added. This approach ensures that optimizations remain isolated within the infrastructure layer, removing the need to retest or alter your business services. To scale right operations, you can offload heavy tasks like processing payments or sending emails away from the user's request using a message broker. The API returns a fast 202 accepted response, while the application layer publishes an event to a queue for background services to process as resources allow. In these distributed setups, developers use dead letter queues to catch messages that consistently fail, ensuring that errors are recorded and can be investigated without losing data. In technical interviews, hiring managers use these architectural discussions to evaluate how an engineer handles system maintenance and long-term complexity. They look for mastery of DI lifecycles, an ability to identify EF core performance issues like N+1 queries, and an understanding of how CQRS patterns fit into the application layer. Mastering the separation of concerns changes how you approach development. You move beyond writing code that simply meets immediate requirements and begin engineering systems designed for technical evolution.